Remainders are flawed for the uniform gauge, yet they're on Euclid built our common stage. Our prime roots shape what we become, irreducible truths that time can't overcome. We embrace classes not congruent to our trace. We dwell with our inverse face to face. When power surge and all seems gone, faith ma points us back to one.
Previously, we introduced modular multiplicative inverses and studied their existence and uniqueness. Special attention was given to the case where the modulus is a prime number. In this section, as an important application, we prove Wilson's theorem, which also paves the way for establishing Fermat's little theorem using a combinatorial argument. To begin, we prove the following lemma. Let P be a prime number. An integer a is its own multiplicative inverse modulo p, if and only if a is congruent to either 1 or -1 modulo p. The if direction follows by straightforward computation. Assume that a is congruent to 1 mod p, or a is congruent to -1 mod p. Then, squaring both sides shows that a squared is congruent to 1 mod p. This confirms that a is its own inverse mod p. Now for the only if direction, assume that a is its own multiplicative inverse mod p. That means a squared is congruent to 1 mod p. By the definition of modular congruence, this implies that p divides a squared minus 1. This expression can be factored as a minus 1 times a plus 1. Since p is a prime number, Euclid's lemma tells us that either p divides a minus 1, in which case a is congruent to 1 mod p, or p divides a plus 1, in which case a must be congruent to -1 mod p. This completes the proof of the lemma. We remind the audience that the only point in the argument where we used the primality of p was when applying Euclid's lemma. Yet this condition cannot be dropped. To see a counterexample, note that 12 is not prime, and 5 is its own inverse modulo 12, yet 5 is neither congruent to 1 nor -1 modulo 12. With this lemma in hand, we are now ready to prove Wilson's theorem, which says the following. Let p be a natural number greater than or equal to 2. The factorial of p minus 1 is congruent to -1 modulo p if and only if p is a prime number. We first prove the only if direction. Assume that p minus 1 factorial is congruent to -1 mod p. We will show that p must be prime. Suppose for the sake of contradiction that p is not a prime number. Then p is composite, meaning it has some non-trivial divisor d, where d is at least 2 and at most p minus 1. Since p minus 1 factorial includes all positive integers less than p, d will show up somewhere in between. This means d also divides p minus 1 factorial. By assumption, p divides p minus 1 factorial plus 1. Since d divides p minus 1 factorial plus 1 as well. Thus d must divide their difference, that is, d must divide 1. This implies that d equals 1, which is impossible as d is at least 2. This contradiction shows that our assumption was false. Therefore, p must be a prime number. Next, let p be a prime number. We want to show that the factorial of p minus 1 is congruent to -1 modulo p. We begin with a concrete example to build intuition. Let p equal 7, and we compute 6 factorial modulo 7, which is the product of 1, 2, 3, 4, 5, and 6 modulo 7. 1 and 6 are each their own inverses. 2 and 4 are inverses of each other. 3 and 5 are also inverses of each other. So, when we compute the product modulo 7, we can group the terms as follows. We isolate the head term 1 and the tail term 6, and we regroup the 4 terms in the middle body into 2 pairs of multiplicatives inverses. Each inverse pair multiplies to 1 modulo 7, so altogether, up to modulo 7, 6 factorial is congruent to the first term 1, multiplying 2 extra ones which come from the 2 pairs of inverses and followed by the last term 6. This is simply congruent to 6, thus -1 modulo 7. The audience should keep this simple example in mind as we now proceed to generalize it to the case of an arbitrary prime number p. Let p be any prime number. If p equals 2, the result states that 1 is congruent to negative 1 modulo 2, which is trivially true. Thus we assume p is at least 3. The factorial of p minus 1 is defined as the product of all positive integers from 1 to p minus 1. Among these p minus 1 numbers, only the numbers 1 and p minus 1 are their own multiplicative inverses, modulo p, as shown in the earlier lemma at the beginning of this section. For each a among the remaining p minus 3 elements, a is between 2 and p minus 2. Since a is coprime to p, a has a unique inverse modulo p as well, namely b between 1 and p minus 1. Now, by the uniqueness of inverses, b can be neither 1 nor p minus 1, so it must lie between 2 and p minus 2. Moreover, since p is prime, b must be different from a. Otherwise, a would be its own inverse, contradicting the previous lemma. As a result, these p minus 3 elements can be grouped into inverse pairs, and the product of each pair is congruent to 1 modulo p. It follows that the factorial of p minus 1 is congruent to p minus 1 itself, which is in turn congruent to negative 1 modulo p. This completes the proof of Wilson's theorem. In the next section, we will use Wilson's theorem to help establish Fermat's little theorem using a combinatorial argument.
신라 텐세